Hi everyone, my name is Ramon Figueiredo. I'm delighted to guide you through this introduction to machine learning and deep learning. As a computer scientist and senior software engineer with expertise in applied AI, I hold a master's and PhD in applied artificial intelligence, specializing in machine learning, deep learning, computer vision, and natural language processing. Additionally, I have served as a professor in the computer science departments of 2 universities, teaching 16 different courses in computer science. Join me as we embark on a journey to explore the fascinating world of AI using machine learning and deep learning. In this presentation, an introduction to machine learning and deep learning will be given, highlighting the evolution of machine learning over the past decades. Concepts, components, and types of both machine learning and deep learning will be explored. Considerations and challenges associated with machine learning, the roles and stakeholders in this field, as well as tools, frameworks, and programming language commonly used in AI will be discussed. Real case studies applying machine learning will be presented, along with insights into how AI can be applied in the film and entertainment industry. Future trends in machine learning and AI will be touched upon. Conclusions will be drawn and resources for further learning will be presented. Machine learning is a subset of artificial intelligence that focus on the development of algorithms and statistical models that enable computers to perform tasks without explicit programming. The primary goal of machine learning is to allow computers to learn from data and improve the performance over time. Here are some key concepts and components of machine learning. First, we have data. Machine learning models require large amount of data to learn patterns and make predictions. This data is divided into training and testing sets. Features are the inputs, variables, and attributes that the model uses to make predictions. Machine learning algorithms are the core of the learning process. These algorithms can be classified into 3 main types. Supervised learning. The algorithm is trained on a labeled dataset, where the input data is paired with the corresponding output labels. Unsupervised learning. The algorithm is given unlabeled data and must find patterns and relationships without explicit guidance. Reinforced learning. The algorithm learns by interacting with the environment and receiving feedbacks in the form of rewards or penalties. The model is the mathematical representation of patterns and relationships learned from the training data. It is what makes predictions and decisions when presented with new and unseen data. During the training phase, the model is fed with training data, and it adjusts its parameters to minimize the difference between its predictions and the actual outcomes. After training, the model is tested on new unseen data to access its performance. Common metrics include accuracy, precision, recall, and F1 score, depending on the nature of the problem. Once trained, the model can make predictions, classification or regressions on the new and unseen data. In many cases, the model's performance is used as feedback to further improve its accuracy. This interactive process is crucial for refining the model over time. Here we can see the evolution of machine learning. Rule-based systems, 1950s, 1960s. Early attempts at AI involved rule-based systems, where experts would manually encode a set of rules to make decisions. However, these systems lacked the ability to learn from data. Symbolic learning from 1950s to 1980s. Symbolic learning systems represented knowledge using symbols and logic. However, they struggled with handling uncertainty and real-world complexity. Connectionism and neural networks. Inspired by the human brain, neural networks emerged as a model for learning. However, during the 1970s and 1980s, interest decreased due to the limitation in the computation power. The resurgence in the late 1980s was driven by new algorithms and increased computing capabilities. Statistical learning, 1990s. Machine learning began to shift towards a more statistical-driven approach, incorporating techniques from statistics and probability theory. Support vector machines, SVM, and decision trees gained popularity during this period. Rise of big data, 2000s. The availability of large datasets and increased computational power allowed for the development of more sophisticated machine learning models. This era saw the growth of techniques like ensemble learning and deep learning. Deep learning from the 2010 until the present. Deep learning, a subset of machine learning, gained prominence with the development of deep neural networks. These networks, particularly deep convolutional and recurrent neural networks, proved highly effective in tasks such as image recognition, natural language processing, and speech recognition. Reinforcement learning from the 2000s until today. Reinforced learning focuses on training models to make sequences of decisions by interacting with the environment. It gained popularity in the fields like robotics, gaming, and autonomous systems. AutoML from the 2010s until today. Automated machine learning, or AutoML, aims to make machine learning more accessible by automating the process of model selection, hyperparameter tuning, and feature engineering. Explainable AI from the 2010s until the present. As machine learning models became more complex, there was a growing need for understanding and interpreting their decision. Explainable AI focuses on creating models that are transparent and interpretable. It's important to mention that the evolution of machine learning continues as researchers explore new algorithms, model architectures, and application in various domains, including healthcare, financing, cybersecurity, and others. Machine learning can be broadly categorized in three main types: supervised learning, unsupervised learning, and reinforced learning. Each type serves different purposes and is used in various applications. In supervised learning, the algorithm is trained on a labeled dataset, where the input data is paired with the corresponding output labels. The goal is for the algorithm to learn a mapping from the input to the output, so it can make prediction on new and unseen data. For example, classification, predicting whether an email is a spam or not. Or regression, predicting the price of a house based on its features. In unsupervised learning, the algorithm is given unlabeled data and must find partners and relationships within the data without explicit guidance. The goal is often to discover the inherent structure of data, such as grouping similar data points. Examples: clustering, grouping similar customer purchasing behavior without predefined categories. Dimensionality reduction, reducing the number of features in the data sets while preserving important information. In reinforcement learning, an agent learns to make prediction by interacting with the environment. The agent receives feedbacks in the form of rewards or punishment based on the actions it takes. The goal is for the agent to learn a policy that maximizes the cumulative reward over time. Examples: gameplay, training a computer program to play chess or Go. Robotics, teaching a robot to perform tasks by trial and error. There are also other specialized types and variations of machine learning. Semi-supervised learning. This type of learning falls between supervised and unsupervised learning, where the model is trained on a dataset that contains both labeled and unlabeled examples. In self-supervised learning, the model is trained to predict part of the input data from both parts of the input data, effectively creating its own supervision. Transfer learning involves training a model on one task and then using that knowledge to help with learning a new but related task. Ensemble learning involves combining the prediction of multiple models to improve overall performance and generalization. These types of machine learning are not mutually exclusive, and hybrid approaches are often used in practice to address specific challenges. Here are key components and steps in supervised learning. Data collection. Gather data that includes both input features and their corresponding output labels. The dataset is divided in two parts: a training set used to train the model and a test set used to evaluate its performances. Input features. These are the variables and attributes of the data that the model will use to make predictions. Output labels. These are the desired outcomes or predictions that the model aims to learn. Model selection is where you choose a type of model or algorithm suitable for the task at hand. During the training phase, the algorithm uses the labeled training data to learn the relationship between the input features and the output labels. The model adjusts its internal parameters based on the training data to minimize the difference between its predictions and the actual output labels. The loss function measures the difference between the predicted output and the true output for each example in the training data. The goal during the training is to minimize this loss, guiding the model towards more accurate predictions. Optimization algorithms, such as gradient descent, are employed to interactively update the model's parameters in the direction that reduces the loss. After training, the model is evaluated on a separate validation set to ensure that it generalizes well to new and unseen data. This helps in tuning hyperparameters and preventing overfitting, the model memorizing the training data instead of learning the underlying patterns. Testing. The final steps involves evaluating the model's performance on the test set, which was not used during the training or validation. This provides an unbiased estimate of the model's generalization performance. Once the model is trained and validated, it can be used to make predictions on new and unseen data by inputting the features without known output labels. Here are some key concepts within unsupervised learning. Clustering involves grouping similar data points together based on certain features or characteristics. Common algorithms for clustering include k-means and hierarchical clustering. Dimensionality reduction. Unsupervised learning can be used to reduce the number of features in the dataset while preserving its essential information. Principal component analysis (PCA) and T-distributed stochastic neighbor embedding (TSNE) are examples of dimensionality reduction techniques. Unsupervised learning can also be applied to identify unusual patterns and outliers in the data. This is particularly useful in detecting anomalies that might represent errors or noteworthy instances. Association rules learning. This involves discovering interesting relationships and associations between variables in large datasets. A priori and eclat are examples of algorithms used for association rule learning. Unsupervised learning includes generative models, which learn the underlying distribution of the data and can generate new or similar instances. Variation autoencoders, VAEs, and generative adversarial networks, GANs, are examples of generative models. The learning process in reinforcement learning typically involves the agent taking actions in the environment, receiving feedbacks in the forms of rewards, updating its internal state representation, and adjusting its policy and value function to improve future decision making. Here are key concepts in reinforcement learning. Agent, the entity that makes decisions and takes actions in the environment. Environment, the external system with which the agent interacts. State, a representation of current situation or configuration of the environment. Action, the set of possible moves or decisions that the agent can take in a given state. Reward, a numerical signal that the environment provides to the agent as feedback for the action it took in a particular state. Policy, the strategy or mapping from states to action that the agent follows to make decisions. Value function, a function that estimates the expected cumulative future reward for being in a particular state or taking a specific action. Popular algorithms in reinforcement learning include K-learning, deep K networks, policy gradient methods, and more recently, algorithms based on deep learning such as proximal policy optimization and deep deterministic policy gradients. In semi-supervised learning, the algorithm is trained on a dataset that contains both labeled and unlabeled examples. The basis of semi-supervised learning can be understood through the following key points. In many real-world scenarios, obtaining labeled data for training machine learning models can be expensive and time-consuming. Semi-supervised learning addresses this limitation by allowing the use of small sets of labeled data alongside a large set of unlabeled data. Semi-supervised learning algorithms leverage the information present in both labeled and unlabeled data. The idea is that the model can extract useful patterns and information from the large pool of unlabeled data, which enhances its ability to generalize and make accurate predictions on new and unseen examples. Two common approaches in semi-supervised learning are co-training and self-training. Co-training trains on labeled and unlabeled data, interactively adding confident predictions for the improved performance. Self-training starts with a small labeled set and interactively expands it by adding confidently predicted instances from the unlabeled data, enhancing overall model performance. One underlying assumption in semi-supervised learning is the cluster assumption, which posits the data points that are close to each other in the input space, often belonging to the same class. Leveraging this assumption, semi-supervised algorithms are meant to propagate information about the labeled data to nearby unlabeled instances. Semi-supervised learning can be approached using generative models, models that learn the joint distribution of input and output, or discriminative models, models that learn the decision boundary between different classes. Deep learning is a subfield of machine learning that focuses on artificial neural networks and their application to solve complex problems. It is inspired by the structure and function of the human brain, using interconnected layers of artificial neurons to process and learn from data. Deep learning has gained significant attention and success in various domains, including image and speech recognition, natural language processing, and gaming playing. Key components and concepts in deep learning include neural networks. These are the fundamental building blocks of deep learning. Neural networks consist of layers of interconnected nodes similar to neurons that process and transform input data. Neural networks are organized in layers. The input layer receives the input data. Hidden layers process the information, and the output layer produces the final result. Activation function. Neurons in the neural network apply activation functions to their input, introducing nonlinearities to the model. Common activation functions include the sigmoid, hyperbolic tangent, and rectified linear unit. Deep learning models learn from data through the process called training. During training, the model adjusts its weights and biases to minimize the difference between the predictions and the actual outcomes. This is typically done using optimization algorithms and a loss function that quantifies the difference between predictions and actual values. Backpropagation is a key algorithm used in training neural networks. It involves propagating the error backwards through the network and adjusting weights and biases to minimize the overall error. Convolutional neural networks, or CNNs, are specialized types of neural networks designed for processing grid-like data, such as images. They use convolutional layers to automatically and adaptively learn spatial hierarchies of features. Here are a list of CNN applications. CNNs are used for image classification, object detection, image segmentation, video analysis, AI in gaming, animation, and VFX, autonomous vehicles, and more. Recurrent neural networks, RNNs, are designed for sequence data, such as time series or natural language. They have connections that form direct cycles, allowing them to maintain a memory of previous inputs. RNNs can be applied in natural language processing, time series, speech recognition, image and videos capturing, and many more. Transfer learning involves using a pre-trained neural network on a specific task and fine-tuning it for a new and related task. This leverages the knowledge gained from the original task to improve performance on the new task. Now let's talk about challenges and consideration in machine learning and deep learning. The performance of machine learning models heavily depends on the quality and quantity of data used for training. Incomplete, inaccurate, or biased data can lead to suboptimal models. Ensuring high quality and diverse datasets is crucial. Data preprocessing techniques such as cleaning, normalization, or augmentation are employed to enhance data quality. Additionally, acquiring a sufficient amount of representative data is essential for training robust models. Overfitting occurs when the model learns the training data too well, capturing noise and make it perform poorly on new and unseen data. Underfitting, on the other hand, happens when the model is too simple and fails to capture the underlying patterns in the data. Techniques like regularization, cross-validation, and using more complex models can help mitigate overfitting. Finding the right balance between model complexity and simplicity is crucial for preventing both overfitting and underfitting. Ethical concerns arise in various aspects of machine learning, including bias in algorithms, fairness, interpretability, and the impact of AI on society. Developing ethical AI requires careful consideration of bias in training data, transparency in the model decision making, and fairness in outcomes. Continual monitoring and auditing the models for potential bias are crucial. There is also the need for ongoing diagnosis and collaboration within the AI community to establish ethical guidelines and standards. Many machine learning models, especially deep learning models, are often treated as black boxes, making it challenging to interpret their decision and explaining their reasoning. Ensuring model interpretability and explainability is important, especially in critical applications like healthcare and finance. Techniques such as LIME, local interpretable model agnostic explanations, and Shapley adaptive explanation can be employed to provide insights into models' predictions. Training complex deep learning models can be computationally intensive and time consuming, requiring substantial resources. Efficient hardware, parallel processing, and optimization techniques are essential for reducing training time and resources requirements. Transfer learning, where pre-trained models are fine-tuning for specific tasks, can also help alleviate these challenges. Transitioning from a trained model to a deployed, scalable system can be challenging. Integration with existing systems and ensuring real-time performance are common concerns. Streamlining deployment process, optimizing inference speed, and considering the scalability of the deployed model are crucial considerations. Containerization and cloud-based solution can aid in the deployment and scaling of machine learning applications. Machine learning models are susceptible to adversarial attacks, where malicious actors manipulate input data to deceive the model. Implementing robust security measures, such as input validations and incorporate adversarial training, can enhance the reliability of models against attacks. Regular updates and patches should be applied to address vulnerabilities. Compliance with data protection and privacy regularization poses challenges in handling the processing sensitive information. Adhering to regulatory standards, implementing privacy-preserving techniques, and obtaining explicit user consent are crucial for enhancing compliance. Collaboration with legal experts is often necessary to navigate complex regulatory landscapes. In navigating these challenges and consideration, a holistic and multidisciplinary approach that involves collaboration between data scientists, domain experts, ethicists, and legal profession is essential for developing responsible and effective machine learning solutions. The stakeholders in machine learning and deep learning encompass a diverse range of roles and interests, reflecting the multidisciplinary nature of these technologies. Researchers and data scientists conduct research, develop algorithms, and create models. Data engineers manage and optimize data pipelines, ensuring data quality. Data analysts analyze data, pre-process it for models, and provide insights. Business executives and decision makers determine strategy, allocate resources, and make decisions based on machine learning insights. Developers implement and integrate machine learning models into applications. End users interact with applications that leverage machine learning for improved experiences. Regulators and policymakers set guidelines and regularizations to ensure the ethical and fair use of AI technologies. Ethicists and societal impact analysts evaluate the ethical implication and societal impact of AI technologies. Investors provide funding for research, startups, and companies working on machine learning and deep learning. Customers and consumers benefit from improved products and services powered by machine learning and deep learning. Industry experts and consultants provide expertise in implementing machine learning solutions in specific domains. Educational institutions offer training and education in machine learning and deep learning. Hardware manufacturers develop hardware optimized for machine learning and deep learning tasks, such as graphics processing units, GPU, and tensor processing units, TPU. Open source community contribute to and benefits from open source machine learning and deep learning frameworks and tools. Legal experts navigate legal challenges related to data privacy, intellectual property, and liability. Machine learning and deep learning frameworks are essential tools for developing, training, and deploying machine learning models. They provide a set of tools and libraries that streamline the process of building and experiencing with different algorithms. Here I present you an overview of some popular machine learning and deep learning frameworks. Examples of machine learning libraries are scikit-learn, XGBoost, H2O.ai, and Apache Spark MLlib. For deep learning, we have TensorFlow, PyTorch, and Keras. ONNX is used as an open standard for AI model interoperability. OpenCV and OpenVINO are used for computer vision and deep learning. NLTK is used in natural language processing. Finally, the most used large language models are ChatGPT, Llama, Bard AI, and Hugging Face. It is possible to work with machine learning with different programming languages: Python, R, Java, C++, and many more. However, Python is the dominant language in machine learning and data science communities. It has a vast ecosystem of libraries and frameworks, making it easy to prototype, experiment, and deploy models. Here are a few real-world case studies showing successful machine learning and deep learning implementations. Image recognition in healthcare. PathAI uses deep learning algorithms to analyze pathologist slides and assist pathologists in diagnosing diseases such as cancer. The system can identify patterns and abnormalities in medical images with high accuracy, helping doctors make more informed decisions. Recommendation systems in e-commerce. Netflix uses machine learning algorithms to analyze user viewing history and preference to recommend personalized content. The recommendation systems play a crucial role in keeping users engaged and satisfied, contributing to the increased user retention. Natural language processing (NLP) in customer service. Google Smart Reply uses NLP to generate contextually relevant and quick response to emails. This technology helps users respond to emails faster and more efficiently. It is an example of how NLP, natural language processing, can enhance user experience and productivity. Autonomous vehicles. Waymo utilizes machine learning and deep learning to enable self-driving cars. These vehicles utilize real-time data from sensors, camera, and LiDAR to make decisions on navigation, avoiding obstacles, and ensuring passenger safety. Fraud detection in finance. PayPal employs machine learning algorithms to analyze user transactions and detect unusual patterns that may indicate fraudulent activities. These systems help prevent unauthorized transactions and enhances the security of online finance transactions. Speech recognition in virtual assistants. Alexa, Amazon virtual assistant, employ advanced machine learning techniques for speech recognition. It can understand and respond to natural language commands, making it a powerful and user-friendly tool for smart home control and information retrieval. Predictive maintenance in manufacturing. General Electric (GE) uses machine learning to predict equipment failures in industrial settings. By analyzing sensor data from machines, the system can predict when equipment is likely to fail, allowing for proactive maintenance and minimize downtimes. Credit scoring in finance. Zest Finance uses machine learning to analyze a broader set of data points than traditional credit scoring models. These enable more accurate assessments of creditworthiness, especially for individuals with limited credit histories. These case studies highlight the versatility and impact of machine learning and deep learning across various industries and applications. Here are some general information on how machine learning and deep learning are commonly used in film and entertainment industry. Machine learning can be used to streamline the animation process by automating certain aspects such as character movement or facial expressions. Deep learning can contribute to the creation of realistic characters by analyzing and mimicking human behavior, improving the quality of animation. Deep learning algorithms can be employed for image upscaling and denoising, enhancing the visual quality of rendered frames. Real-time rendering can benefit from machine learning techniques, optimizing the rendering process for efficiency. Machine learning can be used for simulating realistic physics in special effects, such as fluid dynamics and cloud simulation. Deep learning can assist in creating more convincing visual effects like realistic fires or explosions. Natural language processing techniques can analyze scripts and provide insights for content creation. Machine learning models can be trained to generate storyboards or assist in scene composition based on the script. Machine learning algorithms can help in content security by detecting unauthorized distribution or leaks. Deep learning can be applied to watermarking techniques to protect intellectual properties. Let's talk about current trends in machine learning and deep learning. Explainability and interpretability. There is a growing emphasis on making machine learning models more interpretable and explainable, especially in critical applications like healthcare and finance. Transfer learning involves using pre-trained models on one task and adapting them to another. This approach has gained popularity, allowing models to leverage knowledge learned from one domain for improved performance in another domain. Automated machine learning (AutoML) is on the rise, simplifying the model deployment process by automating tasks like feature engineering, model selection, and hyperparameter tuning. Reinforcement learning is gaining traction, especially in applications like robotics, gaming, and autonomous systems. It involves training models to make sequences of decisions by interacting with the environment. Generative adversarial networks, or GANs, have shown remarkable success in generating realistic data, such as images and text. They have been applied in creative domains like art generation and content creation. The integration of machine learning models with edge devices is increasing, allowing the real-time processing and decision-making. This is crucial in applications like Internet of Things, IoT, and autonomous systems. As edge computing becomes more prevalent, there will likely be advancement in deploying lightweight and efficient models tailored for deployment on resource-constrained devices. Quantum computing has the potential to revolutionize machine learning by solving complex problems exponentially faster than classical computers. Integration of quantum computing with machine learning algorithms could lead to significant breakthroughs. Research in transfer learning will likely continue to evolve, with more advanced techniques for transferring knowledge between tasks, domains, and event modalities. Future advancements may focus on addressing ethical concerns related to AI, such as bias in algorithms. Efforts will likely be made to deploy more robust methods for identifying and mitigating bias in machine learning models. Meta-learning, or learning to learn, could see advancement where models can quickly adapt to new tasks with minimal data, simulating a form of generalized learning. Integration of machine learning with other disciplines, such as biology, chemistry, and physics, may lead to the breakthroughs in drug discovery, material science, and other scientific domains. It's important to note that the field of machine learning and deep learning is dynamic, and new trends and advancement may emerge beyond the scope of this overview. Researchers and practitioners are continually pushing the boundaries, and the future is likely to bring exciting developments in these technologies. In conclusion, we have embarked on a fascinating journey through the realms of machine learning and deep learning, and revealing the potential and transformative power these technologies hold. As we recap our key takeaways, we understand that machine learning is not a buzzword, but a paradigm shift in how we approach problem solving, decision making, and automation. We have explored the fundamental concepts, from supervised to unsupervised learning, and delved in the intricate layers of deep learning, witnessing the emergence of neural networks mimicking the human brain. The applications are vast and diverse, ranging from image recognition to natural language processing, demonstrating the versatility of these technologies in solving real-world challenges. As we wrap up, let's not view this as the end, but rather than the beginning of a continual learning journey. The field of machine learning is dynamic and evolving rapidly, and its potential is far from fully realized. I encourage you to delve deeper into specific areas of interest, experiment with hands-on projects, and contribute to ever-growing landscape of intelligent systems. In the coming years, we anticipate innovative that will reshape industries in our daily lives. Whether you are a seasoned professional or a newcomer, the world of machine learning invites you to explore, experiment, and push the boundaries of what is possible. By fostering a culture of curiosity and continual learning, we can collectively unlock the untapped potential that machine learning and deep learning offer. For enthusiasts seeking a deeper understanding and further learning, I suggest the following books: Pattern Recognition and Machine Learning, Hands-on Machine Learning with Scikit-Learning, Keras, and TensorFlow, Deep Learning, Machine Learning Yanni. Additionally, I highly recommended courses including Machine Learning, Deep Learning Specialization, Introduction to Artificial Intelligence, Practical Deep Learning for Coders. I also would like to suggest exploring the following websites and platforms: Kaggle, TensorFlow, PyTorch, the Stanford Machine Learning course, the website True Data Science on Medium, the Stanford course on Convolutional Neural Networks or Computer Vision, the website Dive into Deep Learning, and GitHub repository containing codes related to machine learning and deep learning. Thank you for joining me in this introduction to machine learning and deep learning. The future is undoubtedly exciting, and I look forward to experiencing the incredible developments that each one of us contributes to the field of machine learning. Thank you very much.